It's my pleasure to introduce Dr. Phil Muirhead. He is presently a Hubble Fellow at Boston University, just across the river, and in the fall of 2014, he'll be joining the faculty there. So he's a faculty in waiting. We're catching him in this rare transition period. So just as a bit of background, he started off as an undergraduate at the University of Michigan, where he's working with John Monnier on interferometry. Was it near IR interferometry? Yeah, okay. And then from there, he went to Cornell, where he got his PhD, working with Jamie Lloyd. And specifically, he was working on an instrument called TEDI, which is the triple-spec externally dispersed interferometer, which was a new way of measuring precision radial velocities in the infrared. That's what grabbed my attention when I hired him as a postdoc while I was at Caltech. So Phil joined my group, I guess, about 2 years ago. And nominally, I hired him to work on an instrumentation project that I'm working on myself. I needed to bring in an expert, so I hired a postdoc. And I learned a great deal from Phil. And my general philosophy for the postdocs that I've hired so far is to just find talent that and give them lots of room to excel. And then let them make me look really good. And then eventually get them off somewhere else where they can become my collaborator. And Phil has done each one of those steps excellently, and I'd like to thank you for that. And I will now pass off to you. He's going to talk to us about small stars and their planets.
Thanks a lot, John. Can everybody hear me okay? This first slide is a NASA illustration of a small star. This is Kepler 42. It used to be known as KOI 961 numbers. And it has 3 very small planets. These are all sub-Earth-sized planets. One of them is about the size of Mars that are illustrated here with this sort of gray, brownish opacity. We have absolutely no idea what the color is. But this particular small star with its small planets does have important consequences, very important consequences. And I will get to that in a minute. And I have a lot of collaborators who are mentioned here, but I'm going to mention, I think each one of these collaborators I'm going to mention individually throughout my talk, so I won't list them verbally. But before I start, I have to start with this obligatory histogram. Many of you have seen this back. I mean, whenever someone gave an exoplanet talk 5 years ago, they'd always show this. It's less common today because exoplanets is really a established field at this point. But it's important to see that extrasolar planets is actually still being discovered and new types are being discovered. So this is a plot of the number of confirmed extrasolar planets around other stars versus the first publication year for that exoplanet. And in red, we have all exoplanets discovered. And over here, you have the pulsar planets and a lot more just exponentially rising. In blue, you have transiting planets. And in green, which is very exciting, you have transiting exoplanets smaller than 2 Earth radii. So there's a large exoplanet community here, but I should just go through and remind everybody of the history in case you're new to exoplanets, which I'd be surprised. But the first detection of an exoplanet around a sun-like star is usually considered this one in 1995 by Michel Mayor and Didier Queloz. Oh, so that's true. Dave, I'm sorry, you're off this plot. I used exoplanets.org.
I don't know the inclination yet. I'm waiting.
I should say that if I'd used the European catalog, Dave would, in fact, you would be first. Down here in 89. So I apologize for that, Dave. That's oversight of mine. Anyway, here, this is the first discovery. And this was made with radial velocities. You look for the tug of the exoplanet on the star. The star wobbles back and forth. You measure the Doppler effect. Here's the plot from that paper. Nice circular orbit. And this, I just want to point out, when you do radial velocities, you measure 3 important things. You measure the orbital period, obviously the period of this velocity signature. You measure the eccentricity, which comes from the shape. And you measure the mass of the planet times the sign of the inclination, which you don't know. Just want to remind everybody about that. Fast forward to 99, and you have the detection of the first transiting planet by Harvard's own Dave Charbonneau. And of course, in this case, you're looking at the planet as it transits the star. You happen to have that chance alignment. You see this dip in the flux, and here you measure another set of things. You measure the orbital period, because this dip happens repeatedly in time. You get the inclination from, well, first of all, you know the inclination is near 90 degrees because you happen to catch it transiting. But you actually get the precise inclination from the shape of this curve, whether it's 89.1 or 89.2 degrees. And you get the radius ratio. So they're measuring different things, the transit and the radial velocity method. I think this is all pretty basic, but it's good to go over it in case you work on something totally different. And then fast forward to last year, 2012, and here you have this little green bar These are the first transiting exoplanets that are smaller than 2 Earth radii. Here is a Nature letter, first authored by Francois Fressin, 2 Earth-sized planets orbiting Kepler 20. So this is very exciting, and this will, in fact, go up this year. I haven't included 2013 because it's not over yet. This will go up, and then I don't know what's going to happen. We might have a little lull in these 2 Earth-sized planets because, as many of you have heard, Kepler has lost its ability to take very precise measurements due to a malfunction in one of the wheels, which is quite sad. Just to remind everybody what Kepler is, it's a spacecraft. It's in an Earth-trailing orbit. It's staring at a part of the sky about 100 square degrees, downloading photometry on 150,000 to 200,000 stars continuously, looking for these little transit signals. Here's a nice paper by Sarah Ballard, an alum of Harvard, PhD alum of Kepler 19. I believe this is a 2 Earth radius planet. And here you have this. You're measuring. Let's see. That's 0.0006 is the dip, which is a far cry from what we have over here, 0.01. Okay, so there are 2 orders of magnitude improvement in the photometric precision since ground-based measurements. So it's fantastic program. Just the facts, it's monitoring roughly 190,000 stars. Of these, to date, there are over 3,000 planetary candidates. Now, I'm going to refer to these as KOIs. They call them KOIs. KOIs can be a lot of different things, but when those of us studying exoplanets, when we say KOI, we're referring to a star with a transit signal, but it's not confirmed to be an exoplanet. Okay, the transit signal could be due to some other astrophysical scenario, but statistically, 90% of these KOIs are likely planets. This is based on a calculation done by Tim Morton and John. And they're 3,000, so this is enormous. This is an order of magnitude improvement over the number of planets detected prior to Kepler. And of those 3,000, over 100 have been confirmed, shown that there's a less than 1% chance that there was an astrophysical signal mimicking the transit is a bona fide exoplanet. And so here's a very nice picture from the Kepler team. This is a sort of a press release image showing all the different stars that they found these candidates around. These are the candidates, not the confirmed planets. And here you have, really big. These look like subgiants over here, and you have blue A stars and things like that. The stars that I'm interested in, that I'm talking about, are way, way down here. These are the smallest stars. These are the M dwarf stars. Okay, the ones that are less than half a solar mass, less than half a solar radius, but are still burning hydrogen, so they're still on the main sequence. So why am I studying M dwarfs? Well, if you go to your neighborhood HR diagram, and this is an HR diagram. This is a picture I snapped with my phone. This is an exhibit at Griffith Observatory in Los Angeles. If you're in Los Angeles, you should check it out. I really like how they do public dissemination of astronomy. I actually really enjoy it. They have this nice exhibit, which is in the corner of some room, and here you have the main sequence. You have these big, bright, B stars and A stars, and they can't even fit supergiants in here, so they use the corner to get the piece of the supergiant. Here you have, I guess this is a subgiant. Oh no, looks like Arcturus. So that must be going up the giant branch. And then way down here, way in the corner, you have relegated to the corner. You have these M dwarfs, these little red dots, right? And they're way, way down there. You really have to try to see them, given all these much more luminous stars. And then in parentheses, so red dwarf is the term used for the public. I say M dwarf. We like to use red dwarfs in public talks. In parentheses, you have very, very poor resolution because of my iPhone, 72% of all stars. And that seems very important. It seems too important to be all the way in the corner in parentheses, trying to hide this fact. But this is extremely important. This is very important. If you look at the initial mass function, most of the stars in the universe are M dwarfs. And this is a nice slide made by the Recon Survey of Todd Henry at Georgia State. They're assessing all the nearby stars with parallax measurements. And these are all the objects within 10 parsecs of the sun. And you see we are dominated by number by the M dwarfs. Okay, so most of the nearest stars are M dwarfs. And this leads to some very fundamental questions, two of which I'll list here. So the first question is, how common are different types of planets around M dwarfs? If a certain type of planet is common around M dwarfs, whether it's a really hot planet orbiting close in, an ice planet orbiting far away, a nice temperate planet that could conceivably host water on its surface and maybe even life. Whatever that type of planet, if it is common around M dwarfs, it follows that it's common in the universe because M dwarfs dominate stellar populations. And that's very important. Okay, that's a huge, that wags the Drake equation a little bit if you think about it. And then the next question is, okay, so what are common around M dwarfs? And then where are the nearby ones we can study in detail? So where are those M dwarfs, or those planets around M dwarfs that we can study like we study the planets in our solar system? Excuse me. So where are the ones that we can, you can have a whole department studying Jupiter, and you can have a whole department studying this exoplanet orbiting this nearby M dwarf, make it Barnard star, Kapteyn star. Where are those nearby ones? So Kepler can answer these questions because Kepler is looking for planets around a large number of stars. They can certainly answer this one, how common they are. The second one is much harder. We'll get into that. But they should be able to answer this first question. But there is a problem. And the problem is the stellar parameters assigned to those M dwarfs that Kepler is observing, those little circles at the bottom of that press release image, the stellar parameters assigned to those stars are weird. They don't make a lot of sense from the Kepler info catalog. They don't follow what we expect for stars. And that's illustrated very clearly in this plot. So this is from Baruchi et al., 2011. This was, I think, the first paper that cataloged all of these KOIs, all of these stars with planet candidates. And I just downloaded it from the paper. And I made a plot of the radius of the star versus the temperature, effective temperature assigned to that star for all the M dwarfs. That is, for anything less than, I think I chose 4,400 Kelvin. I chose some temperature that would correspond to the beginning of the M dwarf sequence. And what you see here is a scatter plot. Now, what you'd expect, and I'm being very pedantic here, but just so we're all on the same page, what you expect is a line. All right, smaller stars are cooler. Right? You expect there to be you expect this to be an HR diagram, and it's a scatter plot. And you certainly do not expect stars with something like 3,700 Kelvin to be this large. So something is funny here. And this is extremely important, obviously, because when you measure a transit signal, like this is from Sarah Ballard's paper, when you measure the transit, you're measuring the radius ratio between the planet and the star, right? You're never actually measuring the true planet. This is just geometric. So in order to infer a radius for the planet, whether it's Earth-like, Neptune-like, sub-Earth-like, super Earth-like, you have to have an accurate measurement of the star's size. So I went over that. That's very pedantic, and I apologize if that's boring to you, but it's very important to know the radius of the stars, and we just didn't know them. So why is it so hard to measure radii of M dwarfs? So this is just a slide. Here's a picture of the transit of Venus. I think this is from 2003. So you have a sun-like star, and over here I've made some PowerPoint circles illustrating the relative sizes of M dwarfs through the M dwarf sequence. So here you have an M1 star, and I've also drawn a little circle indicating a planet. This is Kepler 45. This is a result by John Johnson. Here you have an M4 in the middle of the M dwarf sequence, and it's 3,200 Kelvin. And here you're at the very end of the M dwarf sequence. And there's a lot of physics happening across this single letter, okay, of our spectral sequence. There's a lot of physics. It's not simple. So an early M dwarf is very similar to the sun in its structure. It has a radiative interior. It has a convective exterior. But as you go down in mass, you lose that radiative interior, and the stars become fully convective. And then you have a dramatic change in the radius versus temperature. And then as you get to the end of the M dwarf sequence, you start to have degeneracy pressure, things like that affecting the radius. And so here you have very little change in the radius. In fact, they all kind of plummet on one Jupiter size, one Jupiter radius. There's a lot of physics happening here, and you have to know all of it in order to get the radii right. So some more things that make it difficult. This is a plot of some spectra taken by the California Planet Survey. This is wavelength. These are 3 regions of wavelength. In the visible, here you're at basically 5,000 angstroms. In black, that's a spectrum of the sun. Okay, the black lines are a spectrum of the sun. And the spectrum of the sun does what you've learned in class. You have a continuum with lines superimposed on them, just from Kirchhoff's laws. You have cooler gas on the outside of a star. Inside you have hotter gas that has pressure-induced opacity, stuff like that. So you have a nice black body inside, and you have these cool atoms on the outside making lines. We can model the sun spectrum exquisitely well, extremely well. But when you go to the M dwarfs and you take a spectrum, it's a total disaster. So these are, the red and the blue are M dwarf spectra. And you see there's just no clear continuum. There's just constant lines everywhere. And the reason is, when you get down to the temperatures at the beginning of the M dwarf sequence, you start to have molecules in their atmosphere. And molecules make lots of lines, right? You have a molecule, you have rotation, you have vibration, you have that combined with electronic transitions, and you get this whole disaster. And we don't have accurate, we have accurate models of the sun. We can take a computer and reproduce the sun spectrum. We don't currently have the ability to model M dwarf spectra. Now, there's a lot of effort to do that, and they get close. They see the rotational bands from CO or whatever molecule. But to accurately model everything is very challenging, and that's what we need to do to measure the temperature of the star, and then to infer a radius. And this I already mentioned. I just wanted to mention here again that between these two points in the M dwarf sequence, you go from having a radiative interior and a convective outer layer to just being convective. So you want to go get the radius for an M dwarf. You go take a spectrum, right? And it doesn't line up with your synthetic spectra, but you get some temperature, 3,300 Kelvin. You get some temperature out. Notice that here I've put the effective temperatures along with the spectral types. And M1's somewhere around 3,800 Kelvin, and M4 is around 3,200 Kelvin. Over only 600 Kelvin difference, you have a change in the radius of a factor of 3. 600 Kelvin is a factor of 3 in the radius change. So you need to measure the temperature of M dwarfs extremely accurately if you want to get a radius. Okay? That's not true for the FGK type stars. Well, it's less true. It's still true, but it's less true because here you have a change of 2,000 Kelvin and a 30% change in the radius. So you have to measure that temperature extremely well, and it's very hard from the spectra. There is a saving grace to determining stellar parameters for M dwarfs. So this is a plot, again, of stellar radius versus effective temperature of the star. I just took the Dartmouth Stellar Evolutionary Database, and I just called all the stars in there, basically of all ages from 1 to 12 billion years. There's no initial mass function in this. This is just all stars in the database. Okay? And I splatter them on this diagram from 1 to 12 billion years. And you notice, if you're dealing with stars that have temperatures around 6,000 Kelvin, there is a decade, basically, of radii that can match that temperature. That's because stars evolve. Stars evolve. These A stars are evolving off. These A and F stars are evolving off the main sequence. And so you cannot determine a stellar radius from just a temperature, right? You need more information for these sun-like stars. For M dwarfs, you have this nice advantage that they don't evolve off the main sequence. In fact, they sit there for hundreds of billions of years. They just kind of hang out here. You can, for fun, take MESA and evolve it over tera years and see what they do. And they just kind of hang out here. They move up a little bit as they get denser in their core, but they just sit there. And these higher mass stars don't evolve above this region. They don't evolve in this region. And so, we know the universe isn't that much older. So if we measure a temperature, we can get a radius. There is one problem, which is the metallicity. So included in this are 4 different metallicities for these stars, initial metallicities for these stars. And you can see that there is some degeneracy with metallicity. So what you need to do to get a radius of an M dwarf is measure the temperature accurately, because this is a steep function. You need to measure the temperature accurately and also measure the metallicity accurately. With those 2 parameters, you can walk over here and get an M dwarf's radius. So this motivated a program called Characterizing the Cool KOIs. Kepler is observing about 5,500 M dwarfs. Well, was observing about 5,500 M dwarfs. If certain white papers are read, maybe there'll be some more. Maybe I'll continue observing them. We'll see. There's a K7M0 boundary. You can be a little liberal and get it up to 5,500. So of those, about 140 show transit signals and are listed as KOIs, planetary candidates, transiting planetary candidates. So the Cool KOI program is a ground-based follow-up study of those systems. So we're going and we're measuring temperature and metallicity, and we're determining the stars' masses and radii, and then using those to get the planets' radii, because you need the star's radius to get the planet's radius. It's a ground-based program. And I want to mention that a number of undergraduates and former undergraduates have been a part of this. This is our paper series. And I just want to mention the first one, Katie Hamron, who was an undergraduate at Cornell. She's now a PhD student at UC Santa Cruz. She was involved in this first survey. Andrew Vanderberg, who's here now. Andrew Vanderberg was an undergraduate at Berkeley. He worked with us on this survey. He's now a PhD student here. And Juliet Becker, we're writing a paper right now based on this survey. She is a senior at Caltech. And they've been instrumental, so much so that second authorship, they really deserve higher than that, actually, to be honest. So what we're using is TripleSpec. TripleSpec is a near-infrared spectrograph on the Palomar 200-inch telescope. I actually worked on it as a grad student, building it at Cornell. This is me in a graduate student uniform, doing some grad work with probably screwing in a screw or something stupid. It gets basically Y through K-band in a single shot at a resolution of 3,000. And here's a nice picture of the 200-inch, very famous telescope. And what we're doing is we're taking K-band spectra, so 2 to 2.5 microns, and we're using techniques developed by my academic sibling at Cornell, Barbara Rojas Ayala. She's now a fellow at CAUP in Porto. She developed techniques to measure M-dwarf temperature and metallicity using the sodium and calcium lines in the K-band. So I showed you the plot of visible light earlier with all those molecules, and they're all just being obnoxious, and you can't isolate a continuum, you can't figure out any equivalent widths. Well, if you go out to the infrared, it gets a little easier. So these are spectra of M-dwarfs, and you see all these little bumps and wiggles. This is not noise. Those are, in fact, molecular transitions, mainly from H2O, and they're all competing with one another, okay, at relatively low resolution, 3,000 resolution. And so what that does is it makes this nice pseudo-continuum for these very deep atomic sodium and calcium lines. And it's just a way, it's an area of the spectrum where we can actually measure equivalent width. That's really all it is. It's just a place where you can come up with an index that will correlate with metallicity. And Barbara's method measures temperature by looking at the deformation of the continuum across K-band. So there's very strong H2O absorption over here between 2.3 and 2.4 microns. And as a star gets cooler, this suppresses the flux here while this sticks around. And so you end up getting a bend in the spectrum. So she uses these three regions and looks for the change in the slope between them to determine the temperature. It used to be called knob until we learned that's not something you say in Australia. So we changed it. It's H2OK2. It's not. That's an old plot. Anyway, you asked for that. Sorry. So here are actually the results from our survey. So we went and took all those 140 M-dwarfs with planet candidates, measured temperatures, and measured metallicities, which are here shown in color. We plot them down on the Dartmouth isochrones. And these are the isochrones that appear to best reproduce what we see around nearby M-dwarfs, where we can actually directly measure the radii with optical long baseline interferometry. They appear to be the best for low-mass stars, although that is a little debatable. I mean, we're using them. Mainly the reason we're using them is because they provide a very nice spread of metallicities. There are other isochrones that people often use. Some are from Lyon, the Baraf et al. Models. Maybe you've heard of those, often used for brown dwarfs. We can't use them because they don't provide a spread of metallicity, and that's an extremely important parameter, as I showed you earlier. So we're using these Dartmouth isochrones. We measure temperature, measure this, read off a radius, and we found some very interesting systems. And here are two. So up here we have KY254. This is a metal-rich early M-dwarf. The Kepler data indicates that it has a hot Jupiter transiting, which might not sound that exciting to everybody. Hot Jupiters, we've known about them for a long time. But in fact, hot Jupiters are very rare around M-dwarfs. And this is, as far as we know, this is the latest type object that hosts a hot Jupiter. And it is very, very metal-rich. And that plays into the planet metallicity correlation, which shows that, there is if there's a metallicity-enhanced disk around a star, it's more likely to form cores that form large planets. And this was a paper by John Johnson. And then down here, at the very bottom of our survey, there's this really exciting guy. This was KY961. It eventually got a Kepler number, Kepler 42. And this actually has 3 transiting signals. And this, when we got the spectra and we learned about the size of the star and we refit the transits, and we got these little tiny planets. We published a paper, and it got some press. A number of people were involved in this. Josh Carter was heavily involved in this, as well as John and Kevin Apps, who's an amateur astronomer in England. And we have these nice press images, which are fun. So here is Kepler 42, B, C, and D in relation to other planets. And this little guy over here is just a little bigger than Mars, which was exciting because no planet this small had been detected, except for if you discount the pulsar planets, which are very small. But what's more, this plot's nice, but what's more interesting is if you compare it to, you compare this system, these are very short period planets. If you compare it to the Galilean moons of Jupiter, there's something interesting here. So this is a plot, this is a figure made by a graduate student at Caltech, Katie Kaufman, comparing the separation of these three planets, which when we published they were 1, 2, and 3. Now they're B, C, and D. That's fine. Comparing their distances to the distances of the Galilean moons. And there's a museum trick done in this image. The Galilean moons are not, in fact, this close to Jupiter. The orbital distances are scaled to one another, and the sizes of the objects are scaled to one another, but the orbital distances are shrunk by a factor of 5. So in fact, it's all spread out. Okay? But nevertheless, you see there's some relationship here, and it makes you wonder, okay, so are the physics, could there be some relationship? Could the physics that go into the formation and evolution of the Galilean moons be related to these small planets around M dwarfs? I haven't really thought much beyond that, but it is kind of fun to look at. What is fun is that there are more systems like that. So down here in the mid-M dwarf regime, we're finding more short-period sub-Earth planets. And it's not entirely clear if those are common around mid-M dwarfs or if they're common around all stars. These are just the only ones that we can detect with Kepler. We don't really have statistics on the short-period sub-Earths yet, but it is exciting. This may be a common class of planet. And by the way, this is the peak of the initial mass function. So these are maybe very common systems. So Juliet and I were writing this paper, but then we got severely distracted by this other object, which turned out to be very interesting for entirely different reasons. Over here you have a metal-rich mid-M dwarf, which has a 2% transit depth in a 1.38-day period. So we initially thought this might be another M dwarf with a hot Jupiter, a very rare object, and the latest M dwarf with a hot Jupiter. But something was really funny about it. The transit signal didn't make a lot of sense. So this is the plot of the transit signal, and those of you who do transits already see what this is. The problem is the ingress time is about a 60th of the duration, and you would not expect that for a hot Jupiter. I mean, if you imagine this big thing moving across the star, the ingress time should be something a factor of a few. It should not be so short. And just to remind you of what normal transits look like, here's the Charbonneau 2000 transit curve with this long ingress. And there's also this curvature due to limb darkening as the planet moves across the surface, and we don't see that either. And so our interpretation is a white dwarf around an M dwarf, and we have plenty of data to back that up. Juliet was able to measure radial velocities of the system using our TRIPLESPEC data, low-resolution data. And so we have these nice radial velocities of the M dwarf, okay, the M dwarf component. And they're going up and down by an enormous amount, supporting the white dwarf interpretation. What's also interesting is that the times, the ephemerides of the occultations are 180 degrees out of phase with what you'd expect for a transiting planet. So clearly the object is going behind the M dwarf rather than in front of it during the occultation events. What was really exciting is when you go and you look at the halfway points in between those deep occultations, we see a transit signal, which is very shallow. Here it is. And what we expected, given a white dwarf, was something along the dotted lines. Okay. What we see in our best fit is the solid line, and we are attributing that to gravitational microlensing during the transit of the object. And as far as we know, this has not been definitively detected in this type of system until now. It's been inferred in other systems, but it's never been definitely detected. And we told NASA about this, and they made this fun video, which is the best part of this whole project was the video you get out of it. That's actually not true. There's interesting science, too. But I will show it to you. They took a little, Robert Hurt made this, and he had some artistic liberty. So here's the white dwarf as it moves across, and here it's going to lens the star just a little bit. Now, for those of you who study lensing, let's see, can I go back? I want to just pause this at a certain point. you'll notice something. It doesn't look like a typical lens. Because typically, when there's a lens, you see the Einstein ring being lit up, right? The Einstein ring gets lit up, and that's the source of all the extra flux. In this case, and this is not quite true in the artistic rendering, but it is true in physics, the Einstein radius is actually within the white dwarf. You're only seeing the wings of the lensing, and it's barely filling in the transit. And that scenario is actually written into a paper by Eric Agol from 2002. When you have a very weak lensing effect, you can actually get away with some very simple mathematics. A lot of things cancel and fun stuff like that. And we got to use that to our advantage. And this helps you determine, the filling in of the transit helps you determine the mass of the white dwarf empirically. And so this is from our paper. This is KOI 256, that's the name of it. And we have all of these orbital parameters with no models used in the system at all. The lensing gave us a mass for the white dwarf, which when combined with the radial velocities that Juliet measured, gave us independent masses. The occultation events give us radii. And unfortunately, it's not a very sexy white dwarf. It's a carbon-oxygen white dwarf. It's consistent with models. But it was still kind of fun to do. One more fun part about this is that we measure the period to about a second precision. The reason we can do that is because this is so incredibly sharp. This is about 90-second ingress. And you have that every 1.37 days for many, many, many quarters. You can measure the period of the system quite accurately. We were sort of hoping that we might see some evidence for a planet orbiting the system because you would see delays in the occultation events, but we don't actually see that, which is a bummer. Oh, here's another fun video. So this is a video where every single frame is a snapshot of Kepler data, and the occultation events are centered here and here for each snapshot. And what you see outside of the occultation event, you see this modulation. This is due to rotation of the M dwarf, synchronous with the orbit, because they're so close, they're synchronously rotating, and spots on the surface of the M dwarf. This is our interpretation. And what's fun is, when I play this video, you'll see that, in fact, that modulation will change over time. You also see flaring events that pop in. That's kind of fun. But you'll see the modulation will change, and it'll, in fact, be this looks at first like maybe there's one spot structure on one side rotating around, but eventually it'll change so that and I can try to pause it, you see that, in fact, it's consistent like here. It's consistent with two spots. So here's a minimum and here's a minimum on both sides of the M dwarf. And this is, we haven't really, I made this video, but I haven't done much science with it, but there's a lot of science in here. If you think about, what's the time scale for spot structures to change on a star, this lets us measure it. And a lot of it's enabled by these occultation events, which allow us to pin down the rotation of the star. And there's also all this flaring. We haven't even done this yet, but we could try to correlate flaring with spot position. Are the flares occurring near the spots or on the other side of the spots? There's just a lot of fun stuff to do with the system, which we haven't done yet. One thing I talked about at the ITC lunch, I'll just mention here, is that this M dwarf white dwarf system, the M dwarf is very metal rich. Along with some other systems we measured, this might, we're starting to see some correlation showing that M dwarfs with white dwarf companions appear to be systematically metal rich. Maybe that's due to pollution. I brought that up at the ITC lunch, and I got some really great feedback. Anyway, that was a huge digression. But white dwarfs are cool. They're like planets, but they're more massive. So here was this question I started off with. How common are different types of planets around M dwarfs? And if they're common in the universe. So we actually are addressing this issue. And my office mate, John Swift, who I believe is coming here to Harvard sometime this year, published a paper that concerned itself primarily with this system, Kepler 32, where he was studying how common the system would be. He did a lot of interesting things with it. But as an aside, at sort of the end of the paper, he took all of our stellar parameters from the spectroscopy and our planetary parameters, and he played with different planet populations around all of the stars that all the M dwarfs that Kepler's observing, to try to figure out how common planets are around M dwarfs. And he landed on a very exciting result, which is we expect to have one planet per M dwarf with a period of less than 50 days. So I just don't even read the plot. Just read this. This is the part to take away from it. And not long after that paper came out, a student here, Courtney Dressing, published a very interesting paper where she took the photometry and estimated temperatures for all the stars, used a prior to get the metallicity, which is very important, and got a very similar result. This is a plot of number of planets per star versus planet radius for M dwarfs, and the black line is for periods of less than 50 days, and here are different planet radii. But if you add this up, 0.2 plus 0.3 plus 0.2 plus 0.2, you're getting to 1 planet per M dwarf, which is very exciting. And these are, terrestrial-sized planets, by the way. So that means if you take this plot, all the stars within 10 parsecs of the sun, and you look at all the M dwarfs, all of these likely have planets. All of those M dwarfs that you learn about, Barnard star, Kapteyn star, GJ411, pick your favorite one. 80 Leo, these Proxima Centauri, these likely have planets. It's very exciting. So this leads to the next fundamental question: where are the nearby ones that we can study in detail? So NASA, in fact, thought about this a while ago. This is a poster at JPL that's kind of fading, and I took a photo of it with my phone, and it shows the timeline for NASA's investments to not only discover nearby planets, but also characterize them and search for life. Okay, very ambitious plan. So here you have the Keck interferometer, which was built to measure exozodiacal light around sun-like stars to figure out if that was a significant noise source for detecting Earth-like planets. Here you have Kepler, and I want you to notice what it says about Kepler here. It says statistics of planetary systems. Kepler's purpose was not, and is not, to find nearby systems. It's to go deep, look deep through the Milky Way, collect up enough stars so that when they find planets, they can do statistics of them, not find individual nearby ones. That's a very important point. But Kepler, the results from that were to inform SIM, which is going to discover the nearby systems, and you keep moving up and it gets really kind of cool. You have TPFC and TPFI designed to study the atmospheres of planet hosts and actually look for life. Now, many of you were giggling when I showed this poster, and you know why, because, of course, the decadal survey did not give this plan a very favorable, did not actually recommend it, and in fact killed a lot of these things. So SIM, of course, we all know, and TPF is pushed off into the future so far that it's unlikely to happen. And instead, they recommended that we still approach this problem, but take a different angle. Okay? And they said that, we fully expect the radial velocity technique, finding planets through the orbit of the stars, to achieve a precision to find Earth-like planets. And that precision is about 10 centimeters per second. It's very difficult, it's very ambitious, but that's what they said. And those systems that would be discovered, if they're transiting, instead of launching something like TPFI or TPFC, you would use JWST to take spectra of them because it has the sensitivity. And in fact, it's changed even more now. Now there's star shades and things like that that are being considered. What I want you to concentrate on is this replacement of SIM with radial velocities. And that might sound crazy, but it's not for the M dwarfs. It's not crazy. If you look at the nearby M dwarfs that have planets that have been studied in detail, there are 3, as far as I know. There are a few more that might sneak on here. I guess there's WASP 80, which I didn't include. But these 3 have been studied in detail. You have GJ436b, you have GJ1214b, which was found by the Harvard team, and then you have this new guy, GJ3470b, which is also very exciting. Now, in the era of Kepler, it's hard to imagine that you would find planets first with radial velocities, because Kepler's finding all these planets via transits. But in fact, 2 out of 3 were found with radial velocities first. These are transiting systems, but they were discovered with radial velocities first. And the reason is, M dwarfs are scattered all over the sky. Okay, so it's very hard to build a system to search for transits. Now, TESS is a system to search for them, but I'm going to have to ignore that till the end of my talk. But with radial velocities, you don't have to catch the transit, and you don't have to have a wide field survey. You can go pick off the M dwarfs and take radial velocity measurements at your own cadence to find the planets. And just to remind everybody, these systems are the most exciting in terms of characterizing the atmospheres. Here's a nice result from Zach Berta showing a spectrum of GJ1214b, which basically says it's flat, which says that it's not a solar composition, But this is the next step. This is the next step of exoplanet characterization. And now 1214b was found with the transit survey, but these other two were found with radial velocities. So how do you go about finding planets around M dwarfs with radial velocities? This is a plot from a paper by a student at Caltech, a PhD student named Mike Bottom, and myself. John Johnson's on this paper as well. And this shows this is effective temperature of a star versus wavelength of a spectrometer that you would use to find planets. And the light colors indicate the best regions to use to take radial velocity measurements. So for sun-like stars, over here, the best place is around 500 to 600 nanometers. That's where high-res operates. That's where HARPS south and HARPS north operate. But when you get down to M dwarfs, when you get down to M dwarfs, you actually want to be out in the near infrared because that's where the black bodies peak. That's where there are a lot of absorption lines. And this motivated my PhD project, which I want to mention. It was called TEDI. It was actually had two names. One was externally dispersed interferometer. That was for the instrumentation conferences. For the exoplanet conferences, it was the Exoplanet Discovery Instrument. And this was the combination of an interferometer with TripleSpec. So I described TripleSpec earlier, infrared spectrograph, moderate resolution. When you toss a Michelson interferometer in front, you become very sensitive to radial velocities. And here's a little cartoon made by Dave Erskine, which shows what's happening. The starlight's coming in, you split it in two, you recombine it, and then you go through your spectrometer, and you get this thing that looks like a moire pattern. So I'm going to explain how this works. Here's a little snippet of a spectrum of an M dwarf in H-band. So here at 1.7, 1.725 microns. This right here is a model. This is not data. This is a model spectrum of an M dwarf showing all these molecular lines, molecular rotation. Rotation, vibration, all that fun stuff. Down here, this is the spectrum that TripleSpec would get. TripleSpec is only 3,000 resolution. It doesn't resolve all those lines. So it gets this much smoother thing. This is not what you want if you're measuring radial velocities. You want this if you're measuring radial velocities. But the interferometer actually allows you to get access to this high frequency content. So what I'm going to do is I'm going to jump inside this pixel, this TripleSpec pixel. So if I'm going to jump inside here. You see here's this absorption line. This whole thing is a TripleSpec pixel. So TripleSpec doesn't see this line. It sees the flux underneath it. Think of it that way. Okay? But before that, we multiply the spectrum by a transmission comb due to the interferometer. So the Michelson interferometer allows some wavelengths to interfere constructively. Some of them interfere destructively. And this frequency relates to the optical path difference in the interferometer. All right? So what TripleSpec sees is the integrated light of this spectrum times the transmission comb. So TripleSpec is going to see the integrated tan block here. So what I'm going to do is I'm going to change the path length of the interferometer. I'm going to piston it. I'm going to scan it. And up here, I'm going to plot the flux in the pixel, okay, as I scan it across. And as I scan it across, you see that the areas of constructive and destructive interference are changing. And I can even line it up so that you have constructive on top of the line, in which case you get a minimum in the pixel. All right? And as you scan it across, inside this one pixel, you end up mapping out a sinusoid. Everybody with me? Pretty straightforward. Now, if the star has a planet and the planet's orbiting it, you're going to get a radial velocity shift. That's going to shift the absorption line, and it's going to shift the phase of this sinusoid by actually a dramatic amount. Consider that this, I made it 1 kilometer per second to make it very clear. Consider that this is something like 1/20th or 1/30th of the width of the pixel. That's how much the shift is. Very hard to measure. But the change in phase is rather enormous. I mean, it's something like pi/4 change in the phase. This technique gives you access to the RV content through this kind of clever means. But it's actually quite powerful because here is a plot of, this is actual data from TEDI. This is wavelength versus the change in the path difference of the interferometer, and you get these fringes. If you take a line out across the delay, you end up getting this thing that I showed you a second ago. This is a very powerful technique because what you're doing is you're decoupling, let's see if I can, there we go. You're decoupling radial velocity shifts of the star, which is what you're after, from wavelength errors, errors in the wavelength calibration of the spectrograph. This is extremely powerful. So if you went and you kicked the spectrometer and this whole pattern shifted to the left or the right, that is not the same as a radial velocity shift of the star. That is not true of any other high-resolution spectrograph. If you go and you kick harps, you just made a planet around it or something.
No, you're not allowed in the room.
Not allowed in the room. Here you are allowed in the room. So this is very powerful. Unfortunately, we were unable to actually achieve a precision with TEDI to detect planets, but it wasn't because of the technique or the physics of the technique. Here are some measurements from my thesis showing this is Barnard star, very bright M dwarf. This is radial velocities we measured. This is due to the revolution of the Earth and the rotation of the Earth over time. We clearly recovered it, but we see these residuals of dozens of meters per second. We talked about earlier if we want to find planets, well, if we want to find planets, we need to be down at meters per second. And if you plot all these measurements back to back, you can see there's some systematic behavior in the radial velocities. And we were actually able to recover this after the fact through simulations by accurately incorporating effects from telluric lines. So this is a plot of wavelength versus flux. In blue, you have a model of an M dwarf spectrum, lots of lines from all those molecular transitions. In red, you have the M dwarf multiplied by a telluric model. And you can see that in the infrared, you have lines all over the place, telluric lines all over the place. And it makes it extremely difficult to do precision radial velocity measurements. But this instrument actually ended up having some significant impact, at least for me, because I learned a lot. We were able to get to this 35 meter per second precision with no calibration of the spectrometer PSF. And this spectrometer is bolted to the back of the 200-inch telescope. It's flying through the air. There are pixel shifts of several pixels. And we were still able to get to what is equivalently a small fraction of the pixel in radial velocity performance. And we attribute that to this decoupling of radial velocities from wavelength calibration. So this has actually motivated an instrument we got some money for from JPL called LADY. It stands for Lock-in Amplified Externally Dispersed Interferometer. And I'll go into that in a minute. It also motivates building spectrometers at high resolution. Quite simply, if you want to do radial velocities in the near infrared, you need to be at very high resolution in order to remove effects from telluric lines. So LADY is really a fun project. So we got a DRDF grant, which stands for Director's Research and Development Fund. It was a very nice program. Unfortunately, it no longer exists, which is sad. And I'm the PI along with Gautam Vasisht at JPL. We built an optical system where there would be a visible light system where there would be no telluric lines. And we also built it so that we could rapidly, this is an interferometer, and here's a little simple spectrograph with a prism and a shell. Here's a lens and an EMCCD. We built it so we could rapidly modulate the interferometer. So what we're exploiting by that fact that the radial velocity is decoupled from a wavelength shift is effectively lock-in amplification, which was written up by, I just forgot his name, but it's a very, very famous person who I'll remember in a second. Robert Dickey wrote this up originally, who many of you may know. And by rapidly changing the interferometer, we can actually, we think, through calculations that a student at Caltech named Rebecca Jensen-Clem, she's writing a paper, she's the first author of it, our simulations show we should actually be able to get to centimeters per second of radial velocity precision because the act of the interferometer decouples from the systematics. And we're using, to calibrate the interferometer, we're using this really fancy frequency-locked laser, which fires it's a 532 laser that goes through a very specific iodine absorption line and wiggles around the bottom. And that ends up having frequency precision of part in 10 to the 12, which is fantastic. It's $250,000, and the JPL is just loaning it to us. It's a product of SIM, by the way. Lots of great equipment at JPL from SIM. And they're loaning it to us. This is Rebecca of actually wiring it up. And this is a plot from her simulations, which basically show this is a posterior distribution, for those of you who like Bayesian. This is radial velocity versus wavelength offset. And we clearly decouple RVs from wavelengths. We have a single value peak for any shift, for any radial velocity. And so we're hoping to actually take this system to Table Mountain Observatory, which many of you may not have heard of, is actually a 1 meter that JPL owns. They're building a high actuator density AO system for it for lasercom. So this is deep space optical transmissions to satellites. So what they're doing is they're building a system that is actually perfectly suited. Our system right now is very small. It's diffraction limited, and we need a diffraction limited telescope to be able to connect to it. And this is perfect for it. So we're actually going to propose to do this to NASA and NSF. And then the other project that this is inspired is called HiJack. So I'm at BU, and BU just bought in to be a capital share partner in the Discovery Channel Telescope. We have something like 50 nights a year, and I'd like to build a high-resolution version of TEDI, version of TripleSpec, really, that's based on the TripleSpec philosophy, a very simple design, compact, monolithic, high throughput, high resolution. And the way we can do it, actually, is if we take the TripleSpec design and we replace the low order grading with a high order Echelle, there's no reason we can't go from 3,000 to 60,000, even on the same detector. Now, in fact, this design is a little bit out of date, I'm sad to say, but I'm going to go through it anyway, and then I'll explain why it doesn't work. So this is the TripleSpec. This is just a CAD drawing of TripleSpec. You have all your cryogenics. You have these bulkheads. Inside the bulkheads live an optical design, which is illustrated here. You have a entrance window. You have a parabola, which collimates the light. You have a Leo stop to get out the thermal background. You have a reimager slit. There's also optics here to look at the slit, which aren't included. Recollimator, prisms, Echelle, camera. If you can shove into this system somehow this new R6 Echelle grading that Richardson's just come out with, R6 means an incident angle of 80 degrees, so it's like this. Very, very high order. You can, with our 4-inch beam and with the DCT telescope size, go from TripleSpec at about 3,000 resolution up to 60,000 and still fit on a Hawaii 2, barely. So it's a very small slit. It's only 6 arc seconds long, so it's very, very tiny. Unfortunately, this paradigm, this concept, it's not a design, it's really a concept, it doesn't work. And the reason is the Discovery Channel Telescope has very strict weight limits for its instrument ports. It's a very lightweight telescope, and it's designed to have 5 instruments on the Cassegrain focus at once. This thing is huge. It's liquid cryogen. Okay, this thing is something like 600, 700 pounds, and we just can't fit it in. So we're actually approaching with a different design. I didn't have time to include it in the slides, but anyway, so I thought I'd just show you one. But this instrument can do a lot of fun things. There's accurate and precise radial velocities of low-mass stars to look for planets, which I talked about earlier. That's very exciting. But there's also a lot of facility-class science we could do with something like this. I talked about the importance of measuring temperature and metallicity to get an M-dwarf radius. What I glossed over was the fact that alpha abundance in the M-dwarf also affects the radius. And we currently have no way to measure alpha abundances in M-dwarfs. We need high-resolution spectra in order to isolate lines, isolate specific elements. And that's something this thing could do. There's also some fun things to do with Zeeman broadening. If you look at Zeeman broadening, it has a strong wavelength dependence. As you go to longer wavelength, you have more, the lines get broader. So a high-resolution infrared spectrograph could actually map out magnetic field structures on M-dwarfs, which is exciting. Some people here have probably seen the results from CryoRes doing transit transmission spectroscopy of exoplanets. And then the DCT is actually a collaboration with a number of institutes, many of whom could do interesting science with this, including, so Lisa Prado and Kevin Covey at Lowell want to do forming Jupiters around young stars. And there's also groups at Toledo studying brown dwarfs. Anyway, so I'm just about out of time, and I covered a lot of stuff. I just want to go back to these fundamental questions. How common are planets around M-dwarfs? The answer from Kepler is very, very common. I want everyone to leave with that. Definitely leave with that. Now, where are the nearby ones we can study in detail? That is the next step. And these are some ground-based methods to do this. LADES one concept, hijack's another concept. But I cannot give a talk here without mentioning TESS. Because TESS is that thing that observes the whole sky looking for transiting planets. And in fact, what might happen, what may very well happen, is that these ground-based instruments designed to find the planets won't be finding them. They'll be doing the follow-up for TESS. And I am perfectly happy with that. I do not need the discovery paper. We didn't discover Kepler-42. We didn't discover KY-256. Kepler discovered those. We took ground-based instruments and studied them in detail and learned about their physics. And I think that's a fabulous paradigm to go forward studying exoplanets. So I will stop there, and thank you all for your attention.
We have questions for the speaker. Right in the back.
I'm glad you put your fundamental questions back up, because I was going to ask you about that. So you're talking about the results for the KOIs, but and connecting them to the nearby stars, and saying that we know these planets neighbor. But KOI is living in a totally different part of the galaxy from us. So can we really make that connection?
Repeat the question. Sure. Okay, so Trent's question is, Kepler is looking at these stars that are typically far away. can we extrapolate, well, basically your question is, can we extrapolate the statistics that Kepler's finding to the nearby stars? And that's a good question. I would be surprised if they're dramatically different. The main differences between Kepler's stars and the nearby solar neighborhood would be things like metallicity, right? Because the solar neighborhood appears to be a little more metal rich than we'd expect.
What's the typical distance to the sample of indoors?
That is actually, thank you, John. That's a really good point. And you should know this, because you've got some parallaxes up here. Cheap. Right, so the M dwarfs that Kepler's observing, since M dwarfs are intrinsically faint, the ones it can see happen to be closer than the sun-like stars. So these are something like 50 to 200 parsecs away. In fact, Kepler 42, well, Trent knows the exact distance. So I don't want to spoil his paper. But yeah, so it is reasonable to extrapolate them because they're only a few dozen parsecs away. But, the star formation history of the local nearby star, I mean, there's a lot of stuff in there. There's a lot of interesting stuff in there. And if they aren't the same, what's going on? If they aren't the same, that is very interesting, frankly.
How good is the calibration of the local stars with the interferometry results from Chara?
That's a really good question. So it's not just Chara. It's also VLTI has done a lot of work, and there were some measurements by PTI, which is JPL's long baseline interferometry. I think they're pretty good. I think they're good. It's difficult to assess because it's an extremely challenging measurement, and it's very hard to do twice. The ones that have been done twice by different optical interferometers, there aren't that many M dwarfs. They have to be near the equator because the VLTI and Chara have to see them, are consistent, in fact. So
At what level?
Oh, at the, let's see. So here's where it's tricky, because they have to assume limb darkening. And if you change the limb darkening assumptions in your measurement of the radius, you can change it by about 5%. And I think it's consistent within that. So Barnard star has been measured by both PTI and Chara, and I think they both got 0.200 solar radii, something like that. So that alone gives me a lot of confidence in the measurements. Of course, optical long baseline interferometry it's a very tight field. I used to be a part of it. And the same people working on the PTI measurements, designing the baseline correctors, the same people working. So, what's really great is to compare the VLTI results to the Chara results, and I think that will happen. I'm struggling to think of a star that has both, but I'm sure there are some. Yep.
Do you have any ideas on whether individual element abundances can actually affect this relation between the effective temperature and radius, like carbon or whatever? They
can. And yeah. Oh, sorry. The question is, how much do individual elemental abundances affect the relationship between temperature and radius? That's basically your question. And I haven't done the calculation myself, but I've seen talks where they include it. And in fact, my colleague at VU showed a plot where you can change the radii by something like 10% by changing individual elemental abundances in the isochrones. Andrew West showed that plot, this Maui meeting a year and a half ago. So we are operating with the most information we have. We measure total metallicity with a calibration that has scatter. We combine it with temperature to get radius. It is very important to get the elemental abundances. And not only for determining the sizes of the stars and the sizes of their planets, but just for understanding stars, our nearby stars. Like I said, 70% of stars in the universe are M dwarfs, and we don't know their individual elemental abundances. There's a lot of science to be done there.
One last question.
Yeah, so a lot of the compact systems found by Kepler show transit time variations because they're near resonance often. And I can't remember if KY961 is near mean motion resonance or not, but is there any hints of transit time variations that you can use to get the masses of these planets?
For 961, there is not. As far as the last time we looked at it, there was not. They are very close to this. Two of the planets are close to 4 to 1, but they're not exactly in it. And they're just so low mass. I mean, you need mass to have a variation. And these things are, they're sub-Earth size, so they're sub-Earth cubed in mass. When you think about it. Very, very light planets. So we have not seen them. And Josh looked for them when we wrote that paper. And actually, with Trent, we're doing another paper. We're going to follow up and use all the data on 961, including his very cool parallax. And we'll address that. We'll look for that. But I don't think we're going to see. I don't think we're going to see it.
All right. Well, let's thank our speaker.
Thank you.